Grüße from Germany. The Rover team from Dresden presents the Rover for the ERC 2026 named ASTEROPE-III. All of our team members are currently studying at the Technische Universität Dresden, and most of them have already worked on one or more of our rovers. Let's see what their jobs are.
What is my job? The navigation task, more or less. So I mostly care for the software.
My job is to make it more reliable. Because last year it already mostly worked. It got an award, which we are very happy about. But everything was a bit janky, so this year we want to make it rock solid.
My job was mainly just creating like an architecture for the autonomous software and leading the team, organizing meetings, organizing tasks, getting into a process, cutting down work packages.
And normally the job of a subsystem lead would be to supervise and manage the people working in the subsystem. But because of our dwindling team size, I'm also intertwined into the building and development of the system itself, the debugging.
So I'm currently one of the 3 team leads of the Rover. Then I'm technically the leader of the science subsystem. Then I'm also the leader of the chassis, which is in of itself technically also 2 subsystems because it's the main body and the drivetrain. And
I take part in the ERC because I really enjoy the community of this group.
We're building a Rover for this challenge mostly to have fun.
we don't do this because it's easy, but because it's hard.
The challenge gives us a great opportunity to work together and learn from other disciplines.
You not just want to build it, but also present it in some way or test it. And I feel like the Rover challenge is a great thing for that.
In the subsystem we have the drivetrain, formerly called BEMA, Buggy Electromechanical Assembly, where we have our 4 drive and steering pods with integrated 2 wheels per pod. These are there to propel the Rover in every possible direction with every possible translation and rotation the Rover can do in a plane. So we are using a normal gamepad, and this stick does translations, basically forwards, backwards, to the right and to the left. And with this one you can turn the Rover.
Jetzt.
What still needs work?
We're having a great BEMA, so our drive is really good. And the localization also works pretty good in my opinion. We are running 2 Z stereo cams, and using the SLAM algorithm they give us position, but the part that's currently missing or not working properly is the connection between those. So we can localize ourselves and find a path where we want to go, but it is pretty much a challenge for us to follow this path we found by sending some direction vectors or something into the BEMA and it converting it to following the path.
On top of the BEMA there sits the main body with all the important electronics components. For the drive we have a main electronics stack which features all the motor drivers. It also features the battery management system together with the battery. We have our made and self-assembled battery, which is a so-called 24-volt battery. So we use a 6S lithium-ion pack that is directly connected to the BMS, so the BMS does not sit inside the battery. We went for that approach because in the past we had some issues with reliability on the BMS side. From the BMS, the power flows to some row clamps where it gets distributed to the motors of the drivetrain, to the DC-DC converters for all the different lower voltage subsystems, and then it also goes to the arm.
I mean, it's a pretty standard 6-axis serial manipulator with some BLDC motors. In the front there are 2 stepper motors for axis 5 and 6, also servo motor for the gripper, or for other tools we also use servo motors. Maybe one of the special things are axis 3 and 4 because they're intertwined. If axis 3 is turning, then the motor of axis 4 has to rotate accordingly.
Our problem last year was that we had a really well-designed drone and we didn't have any custom software or any autonomous software. So the one thing which is actually nice is that we have a setup working with MATLAB, ROS and Aruku marker detection. And then also just a link from our custom software from ROS to the flight controller with MathLink. That's the thing we're currently working on. We already have the mid-air stability, so the drone is just stable within the air. If we have connection loss or power loss, the drone automatically lands. So if the battery is getting low, it is giving us a signal and then it will just start to land. Also, we have the ability to adjust with one button click, switch back to manual mode anytime we want and anytime we need.
Additionally, in the main body you can find the navigation stack for autonomous navigation and our secondary stack, which features all the so-called secondary features, which is something we can do because we have the generic interfaces. Our generic interfaces, which we have 3 of, are slots in our main body where we can mount different types of attachments, which are the soil sample container for regolith and rock samples, and the drill, and all possible other additions to our rover.
So we have a tube which gets rotated by one motor, and another linear motor moves it down. With a linear rail we can see how far we are already in the ground, and then at a certain threshold it will stop, and then while still turning, pull it back up to have a less resistance. And then there is just a simple spring mechanism. When the tube is pulled far enough, then it will close and capture all the sand in it, and hopefully a nice clear markings with the depth.